Let's use our knowledge of acid-base chemistry to calculate the pH and pOH of a 0.1 molar solution of acetic acid. The first step in any chemistry problem is always to write the relevant reaction. So if we have a solution of acetic acid that is aqueous, then we know that we are taking acetic acid and adding it to water, and it's going to act as an acid because acetic acid is an acid. And so when it acts as an acid, it's going to donate a proton to become the conjugate base, acetate, and the proton that it donates will get donated to the water to form H3O+. Now that we have the reaction written, the next thing to do is to decide if your acid or base is weak or strong. If it's weak, you need to look up a Ka or a Kb because you're going to have an equilibrium problem that you need to solve. And to solve that equilibrium problem, you're going to need some information about that equilibrium, and you're going to need to know the equilibrium constant for the reaction you've written. So acetic acid is one of our weak acids, and so we know that it's in equilibrium with its conjugate base and H3O+. And we're going to need an equilibrium constant, and this is an acid ionization reaction, and so we look up a Ka for acetic acid, and we find in a table of Kas that acetic acid has a Ka of 1.8 times 10 to the minus 5. So I've gathered all the information that I need to solve this problem, and now I need to remember what problem I'm actually solving. So I want to calculate the pH and the pOH. I can see that my equilibrium reaction that I've written has H3O+ in it, and so it's going to be easiest to calculate the pH first. And pH depends on this concentration of H3O+. So I need to find the concentration of H3O+. And to find the concentration of H3O+, I need to solve this equilibrium problem. So we need to write an ICE table. And I'm getting tired of writing CH3COOH, and so I'm going to write HA. Recognize that the A stands for the acetate, plus H2O is going to form my conjugate base, acetate, plus H3O+, with an equilibrium constant of 1.8 times 10 to the minus 5. And I know that initially I start with 0.1 molar of my acetic acid, and I have no acetate or H3O+. I haven't put any of that in my beaker. So to get to equilibrium, I'm going to have to make X of the acetate and X of the hydronium, and I'm going to have to use up X of my acetic acid. So at equilibrium, I'm going to have 0.1 minus the X that I've used up of my acetic acid. I'm going to have X of the acetate, and I'm going to have X of the hydronium. And now I recognize that this equilibrium constant is small. It's less than 10 to the minus 3. And so I should be able to make an approximation that X is small if this problem is set up in such a way that X represents products. A small equilibrium constant makes very few products, so X is going to be small because X represents how many products I make. And so the amount of acetic acid that I use to make X of acetate and hydronium is small compared to 0.1. And so I should be able to write that my equilibrium constant, 1.8 times 10 to the minus 5, is equal to my acetate concentration times my hydronium concentration, product of the products, divided by my concentration of reactants at equilibrium, which I'm going to approximate as 0.1 because I'm going to ignore X relative to 0.1. So divided by 0.1. So to solve this problem for X, I need to multiply both sides by 0.1, and that gives me 1.8 times 10 to the minus 6 is equal to X squared. And so now I just need to take the square root of 1.8 times 10 to the minus 6, and I find that X is equal to 0.00134. Remember that X represents the equilibrium concentration of H3O plus. And so that is my concentration of H3O plus at equilibrium, and my pH will be related to that concentration. So now I just need to take minus the log of 0.00134. And to do that, I'm going to take the log of my answer, and then I'm just going to take the opposite of that value. I'm just going to multiply through by -1, and so I'm going to end up with 2.87, and that is the pH of this solution. So my solution has a pH of 2.87. To find the pOH, again, I just remember that pOH plus pH is equal to 14. And so if I take 14 and subtract 2.87, I will end up with 11.13 as my pOH. And so this solution of acetic acid, which is 0.1 molar, has a pH of 2.87 and a pOH of 11.13. Now it's your turn to find the pH and pOH of a 0.1 molar solution of ammonia. And I will tell you that ammonia has a Kb value of 1.8 times 10 to the -5. If you solve this problem correctly, you should find that the pOH is 2.87 and the pH is 11.13.